Okay.
Let's go.
All right. So, greetings, everybody. My name is Chibuzor Marcel, and I'm the founder and the director of the Pan-African Citizen Science E-Lab. So here is a website of my organization. You can check it to see all the activities that we do there, mostly citizen science related. So today we are going to be talking about on the fourth series on stars. Okay, we are still on stars. We have talked about the first series, the second series, the third series, and now the fourth series. And in the fourth series, we are going to be focusing on neutron stars. So here are the table of content. So I'm going to be introducing neutron stars. Okay, then I will do some revision on the stellar life cycle that gives rise to neutron stars. Then I'll talk about the three main features of neutron stars, and I'll talk about the properties of neutron stars and types of neutron stars. So what is a neutron star? A neutron star is the dense, compact remnant of a massive star that has exploded in a supernovae consisting mostly of neutrons and having a diameter of about 20 kilometers but a mass of about 1.4 times that of the sun. So to bring it in perspective, to make it very simple, a neutron star simply means a dead star that is full of neutrons, okay? Predominantly neutrons, although we have some other particles, but predominantly neutrons. And also, I said neutron stars are dead stars, okay? So just like us, humans, we were born, we lived our lives, okay? Then we die. When we die, we change form, okay? We become bones. So a neutron star is our version of bones. So, but for a neutron star, it is made up of neutrons. So that is exactly, and it is pretty small. So now, which stage of a star gives rise to a neutron star? So starting from the life cycle of a star, stars are born from the collapse of the giant molecular cloud. Okay, so from there they proceed to the protostar stage. Now, depending on the mass, for a neutron star, the progenitor stars are high mass stars. So they proceed towards this direction. So they fuse hydrogen, that they become main sequence stars. They fuse hydrogen to helium and other elements. Okay, so from there the supergiants. So after fusing all the elements in the core up to iron, okay, they explode uh, into supernovae. Now, so supernovae are stars. The progenitor of neutron stars have masses from 8 to 20 solar masses. So when such kind of stars experience supernovae, they become neutron stars. Okay, so that is where neutron stars are coming from. So now there are three main features of neutron stars, which I will be explaining. Three main features. They are small in size, extremely small in size. Okay. They have high spin rate and they have huge magnetic field. I'm going to explain where all of these things are coming from. So starting from the small size. Remember, for for a star, when it is still fusing hydrogen, helium, carbon in the core, okay? So as it is fusing this it up to the level of silicon, okay? Silicon fuses to iron. Now, iron, the energy content in the core of the star is not able to fuse iron to other higher elements, okay? And secondly, iron absorbs heat. And you know, is heat produces the radiation pressure that supports the structure, the edifice of the star. Okay, so when the heat is gone, there's no longer radiation pressure, so the star is going to collapse. The star is going to collapse. So when the star begins to collapse, the electron will fuse with proton to become neutrons, okay? And also there are neutrinos. There are particles called neutrinos, but they are not our focus for today. So, but the major thing is that electrons fuse with protons to become neutrons, okay? Now, these neutrons occupy all the available spaces, you understand, until they become degenerate matter. Let me explain what I mean by this. So let us visualize what is going on. Imagine that you have soldiers. You have these soldiers standing, okay? They are posing at attention. So for these ones here, you see, there are still spaces in between them. Spaces. Even one person can fit into those spaces, okay? Even here. So, but if they experience a force, so imagine them as neutrons, okay? So these are neutrons. So when they experience a force, okay, they are compacted, okay, until they stand against each other, on the shoulders of each other. You know, it's not possible to climb on top. So as I was saying, this degeneracy was proposed by the person called Pauli. It is called Pauli exclusion principle. It states that no two fermions, okay, can be in the same quantum state. So once they attain this state, okay, there is nothing that can be done. So this is neutron. So this neutron supports this degenerate neutron supports the star and no longer the heat, the radiation pressure like for main sequence stars or stars that are about to die. So that is the support for the star. So that is why the star is small. So you have all this matter compressed into a very small size by this gravitational force. Okay, so that is why. Then explaining the high spin rates of neutron stars. Why does neutron stars have high spin rates? So let us start with everything in the universe, be it galaxies, stars, planets, even subatomic particles like electrons and protons, all of these things have spin, okay? So we call that angular momentum. That spin is called angular momentum. So now, in the absence of any external agent, the angular momentum is conserved, okay? This angular momentum is conserved, it is constant, it means it is constant. And here is the formula for the angular momentum. So you have angular momentum L is equals to moment of inertia, okay, I, then times angular velocity, omega, okay? So for a sphere, the formula for the angular, for the formula for the moment of inertia is this, okay? But I'm not saying a star is a sphere, it's a solid sphere, but it is almost like a sphere, okay? However, there are every shape has their own formula for angular momentum. So, but what is important there is the mass and the radius in the moment of inertia. Sorry, moment of inertia. What is important there is the mass and the radius. So imagine that you have the same mass and the size of this sphere increases. So you say that the angular momentum has increased. So that is the size of the sphere increases. So because the radius has also increased. Okay. So here is the formula for the angular velocity. So for this, so I'm saying that the moment of inertia times the angular velocity will give a constant. So it means that it means that it means that imagine at first you have about the moment of inertia is 4 and the angular velocity is 5. Angular velocity is 5. If you multiply these two, it will give us 20. Okay. Now, if the moment of inertia decreases, that means reduction in the size of the sphere or in the size of the star or whatever. Let's say it becomes 2 units. It becomes 2 units. To make this product to be the same value, the angular velocity is going to shoot up, and that is why it is 10. So understand what is at play here. So to maintain this constant value, these two has to be interchanging between each other. So that's exactly what is going on. So I have developed this simulation for you to understand what is going on. Okay, here you have the radius. This is the radius of Earth. I just use Earth, okay, because Earth is spherical. It applies to every spherical object anyway. So the mass is constant. We're not changing anything. We're going to only change the radius. Sorry that you cannot see that, but this is just, trust me. I'm going to play the video and you're going to see what is going to happen right now. So if I play the video, okay, so I'm going to reduce the radius now and watch how the angular velocity is going to increase. It's going to spin faster. You see that? Now I'm going to increase it again. I'm going to increase the radius, I mean, the size of the sphere. It is going to slow down. So I'm explaining to you why neutron stars are high spinning stars. They have high spin rates. So I'm going to reduce it again. So it's going to increase, the spin is going to increase. So that's exactly why neutron stars are the way they are. Their spin rate is very, very, very high. Now, for a newly formed neutron stars, their period simply means the time to make one complete oscillation. Their period ranges from 1.6 milliseconds to about 8 seconds. This is just time for one complete oscillation. It is incredibly fast. Now, the fastest neutron star, we call it PSR. It has a weird name. You can see the name here. So the period is about 1.4 milliseconds. Okay, so it corresponds to about 716 rotations per second. 716 rotations, not even a fan. Both of us, all of us know what 1 second is. 1 second. So in 1 second, this neutron star has spun over 716 times in 1 second. So the spin is insane. Neutron star spin are very insane. But over time, neutron star gradually loses their rotational energy and slow down. I'm going to explain that later, why it slows down. So now let us explain why the neutron star has a huge magnetic field. Let us explain why they have huge magnetic spin. Now, if you remember in physics or in science, okay, charged particles like electrons is negatively charged, protons are positively charged. But what I want to mention here is when particles are in motion, just like in wire, okay, in your wire, when you have electricity flowing through a wire, it generates magnetic field around it, okay? And in the same way, if you move magnets, okay, around a conductor, it generates electricity. So that is just vice versa. It is given by the Maxwell's equation. But the most important thing the emphasis here is on the charge. So the electrons and the protons when the magnetic fields, okay? And that is the cause of the Earth magnetic field. In case you don't know, particles at the Earth, inside the Earth, they're flowing like this molten magma or lava. They are the cause of the Earth magnetic field. So when they move, now, I told you that a neutron star is made up of almost neutrons, and a neutron has no charge. So how come a neutron star has so much magnetic field? So to explain that, to explain that, number one is that neutron stars have inherited magnetic field from the
Marcel, we don't hear you. Marcel, sorry guys, we have some lags, but we are fixing. Just wait. If you have any question, you can make it.
Sorry for the interruption. It's back now. The network is back.
Don't worry. Don't
So,
worry. Let's go.
all right. So, as I was saying, for magnetic field, I said the magnetic field from the progenitor star that gave rise to neutron star is trapped. So I was using a light bulb as an example. So imagine you have a light bulb that is emitting light. Okay, so imagine now you increase the surface area of this light bulb. Now, the amount of the power of the bulb is going to reduce. Okay, the power is going to reduce because of the huge surface area. Now imagine again, you reduce the surface area. You reduce it even lesser than what it was before. You will see that the power will increase. So that is why the magnetic field of a neutron star is amplified. Okay, so another cause of the huge magnetic field, the rapid rotation of these neutron stars. Remember what I said before about moving particles, moving charged particles. When charged particles move, they generate magnetic field. If they move fast enough, the faster they move, the more the magnetic field. Okay, so like I have explained before about the rotation, the high speed rate of neutron stars. So as these neutron stars spin, these particles, these charged particles on neutron stars, the protons and the neutrons, the protons and electrons, they experience acceleration, and so they increase in the magnetic field individually, and by superposition, they increase the overall magnetic field of the neutron star. So the combination of these two magnetic field of neutron stars. So here is the diagram of a neutron star. So neutron stars have layers. First of all, it has an atmosphere. Okay, it has a crust and it has a core. Okay, the atmosphere of a neutron is about 1 to 2 centimeters. Okay, and it is predominantly made up of hydrogen and helium and carbon. Okay, in the state of plasma. Okay, they also have we have outer crust made up of ions, electron gas, inner crust, heavy ions, relativistic electron gas. So talking about density, so I just a neutron star having almost the same mass as the sun, but all of this mass is compressed to a small size of about 10, a radius of 10 kilometers or diameter of 20 kilometers. So that's so I'll talk about the neutron star density. So atomic nucleus, okay, are very dense, okay? Now, neutron stars are comparably as dense as this atomic nucleus, okay? So that is why neutron stars are regarded as the densest object in the universe and not black holes. Remember, when I was teaching black holes, I said black holes are not the densest object, okay? Because they are, all the mass are inserted into a volume, zero volume. So the mathematics would suggest that the density will become infinity, but it does not really happen because the infinite density does not make any sense in physics. So the laws of physics for a neutron star, the laws of physics still works. So if our neutron stars are the densest, according to our known law of physics. They are the densest object in the universe. So neutron stars are so dense that 1 teaspoonful of a neutron star is about 2 billion tons on Earth. To get a perspective of what 2 billion tons mean, 2 billion tons is about 300 Great Pyramids of Giza in Egypt, or 6 Mountain Everest. So here's the picture, the pyramids of Giza, ancient pyramids in Egypt. Okay, so if you get 300 of these pyramids, 300 is equivalent to about 1 teaspoonful of a neutron star, or about 6 Mountain Everest. So that is very close in a neutron star, 1 teaspoonful. So neutron stars are extremely dense. Okay, so they serve as a perfect lab for studying the properties of matters at high densities and pressure, because we can produce this kind of density on Earth in our labs. So that is why studying neutron stars are very important. They help us to understand how these are and pressures. How about gravity? The gravity of a neutron star is so high. In fact, we lack words to explain how big it is. It's about 10 billion times stronger than Earth. 100 billion times stronger. If it takes you a particular amount of energy to climb from the valley of Mountain Everest to the top, that energy is equivalent to walking, okay, about 1 micron on the neutron star surface. 1 micron. So the total energy it will take you to climb from the valley to the top is equivalent to just walking 1 micron. You know what micron means? Very, very. You can't even walk, because the gravity there is so intense. So how about throwing something on neutron stars? So this is an object, okay? So you throw this object far away, not too far away, but just some distance away from the neutron star. So as this object falls, by the time it reaches the surface of the neutron star, it would have attained a speed, a final velocity of about 70% the speed of light. So you can imagine that. So you can just, drop something from wherever you are, you see how fast it goes down. So I'm telling you, if you do that on a neutron star, but the final speed of that object on touching the neutron star will be 70% the speed of light. I remember the speed of light is the fastest thing in the universe. How about if you want to throw it? If you want to throw something off from a neutron star, you will need the same amount of speed. Object an initial speed of about 70% the speed of light. So it is enormous because of the huge gravity. Now imagine that this object is about 10 gram. 10 gram. Just imagine, okay? This is a calculation that has been made. Imagine that this object is 10 gram. Okay, that is the size of a marshmallow. So 10 gram. By the time this object falls to the surface of a neutron star, the energy, the impact energy it will generate is equivalent to the atomic bomb dropped in Hiroshima in Japan during the Second World War. So it is enormous. Just 10 kilograms could generate such amount of energy on the neutron star. It's because of the gravity. So now there is a misconception I see everywhere on social media, and some people talk about it, even some professionals talk about this. So they are insinuating that that enormous energy, impact energy, is due to mass energy conversion. That is not true. It is not due to mass energy conversion. It is not from the mass. It is not, that energy is not coming from the mass of that object, that 10 kilogram object. They say that for neutron star, the object, the conversion will be 70%. Okay, but for a black hole, the conversion will be 100%. But those are not true. Okay, those are not true. These are misconceptions. That energy is coming from the gravitational potential energy of the neutron star. So when the object is in the field, in the gravitational field of a neutron star, it gains energy. So it gains gravitational potential energy. Okay, now it converts, as it is falling, it converts the gravitational potential energy to kinetic energy. That is energy of motion. So as the object falls to the surface, it will convert all of those energy to different kinds of electromagnetic waves. It could be gamma rays, visible light, radio waves, and so on and so forth, and even shock waves. Okay, so the energy is coming from the gravitational potential energy of the neutron star system, and not from mass energy conversion. So also, if you are observing a neutron star, you're going to see 2/3 of the entire surface of a neutron star. So because of the way gravity curves the space-time around the neutron star, 70%. Now, sorry, 2/3. So this 2/3 is not, because if you have a small ball, a small pink ball, okay, tennis ball, you can literally see the surface. You can even see half of the surface, or even more than half of the surface, because of the small size. Okay, and remember I said that neutron stars are small. So the reason why you are seeing to small size of a neutron star is on the surface of a neutron star, it is possible for you to also see 2/3 of the entire surface of a neutron star. So for a black hole, you can see the entire surface of a spot. For a black hole, you can, but for a neutron star, it is just 2/3 of the entire surface. So neutron stars, the gravity also can stretch light. Okay, because I told you 70%. So by the time light must have escaped from the surface, it has lost a lot of its energy. So if a neutron star is this color, let us say the neutron star is in this spectrum, it is blue in color. By the time you see it on from Earth, it has become red because of gravitational redshift. We call it gravitational redshift. Okay. Now we have Doppler redshift, but here this one is gravitational redshift. So don't misunderstand it too. So now clocks tick slower in neutron stars because of the huge gravitational influence. Call that time dilation, gravitational time dilation. So on the neutron star, clock's time, let me just say time ticks 2 times slower than on Earth. So just like black holes, just like if you are falling into a stellar mass black hole, falling towards a neutron star, you also spaghettify. You'll be turned into spaghetti. So that's just the same effect because of the huge gravity of this. Now, Earth has a magnetic field due to moving charged particles in the core. Okay, but it's very weak. It's very weak. Okay, but the weakness is also strong to protect us from the ion
Never give up.
Yeah, we never give up. So,
Never give up.
uh, so I was talking about the MRI machine. It has a very in field about 1.5 Tesla. Then we have the lab magnet, the one used at CERN, the Hadron Collider is around 10 Tesla. Now, the reason why I'm mentioning this is because I want to compare them to the magnetic field of a neutron star. Now, for a neutron star, the magnetic field is between 10,000 to 1 million Teslas. So imagine that. Compare these numbers that I mentioned above to this. The magnetic field is about 1 trillion times stronger than Earth. 1 trillion times stronger than Earth. Now, to understand this thing, to understand it very well, we want to convert magnet to energy. So we pick a volume, 1 cubic centimeter. Let us pick such volume, 1 cubic centimeter, and calculate the amount of energy in terms of magnetic field that is buried there. So if you do the math with the equation, okay, this has been done already, okay? So I'm not going to do them in this presentation. So if you do the math, it is going to give you about 5.6 times 10 raised to power 16 joules. If you still do not understand that, that is an energy that is produced by a nuclear power plant in a year. So an energy produced by a nuclear power plant in a year is equivalent to the magnetic field that can be obtained, the energy in a magnetic field of a neutron star in around 1 cubic centimeter. So that is very insane. So neutron star is a star full of energy. So now this magnetic field emanates from the crust. I've explained that before. Emanates from the crust. How about the temperature? So for a newly formed neutron star, I mean a neutron after exploding in supernovae, okay, the temperature after the explosion is around 10 billion to 1 trillion Kelvin. That is insane. Okay, so like I remember, like I said before, okay, during the collapse of a star, the electrons fuse with protons to become neutrons, okay, and they give rise to neutrons and neutrinos, okay. Remember, and I said I'm not going to talk about the neutrinos because they are not part of our discussion today, but I'm going to mention them now. Now, all of this energy, these 10 billion to 1 trillion Kelvin of energy is carried away by these neutrinos. So So as I said, due to neutrino emissions. So for a middle-aged neutron star, thousands to million years, the temperature reduces further to about 100,000 to 1 million Kelvin. Do you understand? So over the course of a billion years, okay, the temperature reduces below 100,000 Kelvin. However, they are still visible in the X-ray wavelength. So they are still emitting X-rays. So types of neutron stars. So we have pulsars, we have magnetars, we have X-ray binaries, we have millisecond pulsars, we have radio quiet neutron stars, and I'm going to explain them one after the other. So how about a pulsar? A pulsar simply means two things. It means two things. A pulsar means a speeding neutron star, and look at it. Look at the structure here. So you look at, this is the angle, this is the axis of spin, the spin axis. And here you see this magnetic field coiled around it. Okay, this is just a diagram. And now you see these jets here. Okay, now this is the radiation we are talking about that it is emitting. Okay, so if Earth is aligned with these jets. Okay, we see it. So as this neutron star is spinning, okay, these jets are sweeping around Earth. So that is, so when we see them, we say that it is a pulsar. Okay, otherwise it is not. It remains a neutron star. If we do not see this, it becomes it remains a neutron star. So we'll not even be able to know it. So all pulsars are neutron stars. Okay, all pulsars are neutron stars because that is how we detect these things. Okay, so now, so the first set of pulsars that were discovered gave rise to the little green men theory. Okay, because we believe that maybe aliens are trying to communicate to us. So you can imagine something, sweeping across Earth and in a very periodic manner. So it makes sense to believe that maybe aliens are trying to communicate with us. But over the years, we discovered more and more new pulsars. So that claim of little green men was dismissed. So we knew that these are actual stars and not aliens trying to communicate with us. Now, so these pulsating radiations are very periodic, okay? So, and different pulsars have their own, okay? I could have played you some of the sounds, but Zoom will not allow the sounds to be transmitted. So I'm going to use a clap to demonstrate that. I'm going to use a clap to demonstrate that. So some neutron stars have periods like this. Some have periods like this. Some have periods like this. I hope you can hear the sound. So they have different periods. They do not have the same periods. So pulsars are accurate clocks that can be used for interstellar travels. So the universe is even prepared for interstellar travel. The universe is prepared for interstellar travel. And these pulsars were used to demonstrate Einstein's general theory of relativity. So here is the pulsar. So
Yes, it's a malediction today.
okay, I'm back.
No,
So all right. So
don't give up.
oh yeah, I'm not giving up at all, and I'm almost done. Almost done. So I want to demonstrate. Um, I want to explain through this simulation the proof of Einstein's general theory of relativity. Okay. Now follow me. Assuming you are moving in your car and you slam the brake, you just encountered an emergency and you slam the brake. So what happened is that the friction between the tires will dissipate the energy of the car into heat. Okay. Now, so the energy has now been converted to heat and it goes into the universe. That makes a lot of sense. Okay. Now, the same thing also happens with electrons. Okay. When electrons in an atom, okay, when they move to lower energy state, to a lower energy configuration, they emit electromagnetic waves, which makes a lot of sense. Now, how about for two orbiting objects in space, like maybe two stars, when they're orbiting, they are coming closer to each other. So now, what do they radiate to make them to come closer? What they radiate is gravitational waves. Okay, so Einstein's theory was these orbiting pulsars were used to prove Einstein's theory. So as these pulsars are orbiting each other, they are coming closer, and as they're coming closer, they are emitting gravitational waves. And that they come even much closer, they emit more gravitational waves. until they collide and become one. So that's exactly. So it is used, these pulsars were first used to prove Einstein's general theory of relativity. So here is another picture. Okay, this is not a simulation. I want you to see it. So this is the fabrics. Like I told you, space is a material. When I was talking about black holes, space is a material. So you can see, so as these neutron stars are spiraling into one another, they are giving out these gravitational waves. Okay, so now these gravitational waves transmit at the speed of light. So I want you to know that gravitational wave transmit at the speed of light. So magnetars. So we have just finished pulsars. Now magnetars. Okay. So each of these types of neutron stars I'm going to be explaining have something unique. Okay. So but I'm going to use pulsar as a reference. Okay. So right now I want you to imagine pulsar as having the most moderate of everything in terms of moderate spin, moderate magnetic field. Okay. I'm saying compared to other types of neutron stars I'm going to explain. So I'm going to be comparing other types of neutron stars to a pulsar. Now, coming to magnetars. What does a magnetar have that makes it stand out? What makes it stand out is the magnetic field, the enormous magnetic field. Remember, when I was talking about the magnetic field of normal pulsars, I said they range from about 10,000 to about 1 million Tesla. But for a magnetar, the magnetic field is around 100 billion. So it is the most magnetic object in the universe. The most magnetic object in the universe. So let us discuss how they are formed. So they can be formed from core collapse, normal core collapse supernovae, okay? They can also be formed from neutron star mergers. They can form from accretion-induced collapse and the evolution of binary systems. I'm going to explain this one after the other. But in general, so for a neutron star to be formed, the mass of the progenitor star has to be between 8 to 20 solar masses. So I want you to bear that at the back of your mind. So this is the core collapse supernovae. Now, about 10% of neutron stars born through core collapse become magnetars. Okay. Now, to become a magnetar, the progenitor star has to have some things initially. It has to have some initial conditions. Okay. And one of those initial conditions is the spin. The spin of the progenitor star has to be high. Okay, so this is going to be very high because I told you the spin is what generates this magnetic field. Okay, so it has to be high so that when it collapses and becomes a neutron star, the mass of the magnetar also, sorry, the spin of the magnetar also becomes very, very high. And also there has to be some internal compositions of the progenitor stars. So that is these are the reasons. So these are so here is the supernova explosion, neutron star born. This is the simulation of Crab nebulae. This is it. So the spin of the initial mass, the progenitor star, has to be very high for you to give for it to become a magnetar and not a pulsar. Otherwise, it becomes a pulsar. Okay, so that's it. Then, so another way magnetar can be formed is through what we call neutron star merger. These are just two neutron stars that are spinning. I've shown you this simulation before, but here the emphasis is on the merger and not the gravitational waves like I showed you before. Okay, so observe what is going on here. When these neutron stars, when they merge, okay, remember I told you the minimum mass of a neutron star is about 1.4 solar masses. Okay, now if two neutron stars combine together, that should give us around 2.8, which is above the TOV limit, the maximum limit of a neutron star. So now, but if you observe, some of the materials are lost. So not all the materials become form, together. Do you understand? So it is possible that this may not collapse with a black hole. It may still remain a neutron star. So, however, if it remains a neutron star, it is going to be a magnetar. So the magnetic field is going to be very much amplified. So you are combining magnetic field from two independent stars into one. So that is why. So now these neutron star mergers are believed to be responsible for what we call the out-process nucleosynthesis. Okay, so now if you look at the periodic table, you will see that there are elements that are way above iron. Okay, and I told you earlier on that stars are element factories, and I also said that fusion happens until you have ions. Okay, so how about these other elements that are way above iron in the periodic table? Where do we get them? So as I was saying, all the precious elements, the gold, the silver, the platinum, the uranium, all of them were birthed through these nuclear star merger. So we call that the R-process nucleosynthesis. Let me expand my. So now we have accretion-induced collapse. So in here, you have a white dwarf. Remember, a white dwarf is less massive than a neutron star. Now you have this white dwarf somehow stealing some matter from a main sequence star. It is gravitationally tied to that star. Okay, so it is stealing matter from it. Do you understand? So as it accumulates, as it is stealing this matter, the mass is increasing. Okay, it increases to such a point that it will be way above the Chandrasekhar limit. It explodes as a type 1a supernova to become a neutron star, which would ultimately become a magnetar. Okay, so that is why. So that is from accretion-induced collapse. Then we have evolution of a binary system, just almost the same process like this one. Almost the same process as this one, but this case, this is a neutron star that is not a magnetar. This is a neutron star that is not a magnetar. Now, as this neutron star is stealing matter, it is stealing matter from this main sequence star. We call it the donor star. Okay, so now as this matter is coming in, look at this accretion disk. They have angular momentum. I have mentioned that before. As they fall onto these neutron star, they add to the angular momentum of the neutron star. So they spin up the neutron star, and the neutron star becomes the spin becomes so high, and the more the spin, the more the magnetic field. Those charged particles that I told you about, they spin even higher, and the magnetic field of the whole system increases. So, and that becomes a magnetar, because magnetars are known for their intense magnetic field. Now, know that this is very tricky. Okay, this is the same process as a millisecond pulsar. This is how a millisecond pulsar acquires its huge spin. I've not explained it, but only difference is that for a millisecond pulsar, the magnetic field is not amplified. The magnetic field is just normal, but the only thing that is amplified is just the spin. I told you the spin as their relationship. Sometimes some crazy things happen, so it is not all of that obtainable. So other features of a magnet are, now, initial rapid rotation. When magnetars form, they often start with very rapid rotation rate. Yeah, crucial for generating their strong magnetic field through mechanisms like the dynamo effect during core collapse. Now, because of this huge huge this huge spin they have in their initial lifetime. Okay. So their surface is stressed. Okay, if you combine the huge spin with the intense magnetic field or stress, and also the gravity, the surface is under huge stress. Sometimes they crack. Okay, and we call that a starquake. And that is the area I worked on during my undergraduate research. So we call that a glitch. Okay, so the star will crack, release energy, it will spin up. Okay, then it will spin down. To crack again, spin up again, then spin down even lower than it was before until it loses a lot of its rotational energy. So magnetic braking, the powerful magnetic field of magnetars exerts significant torques, causing them to lose rotational energy much faster than typical neutron stars. This rapid spin down leads to longer rotational periods over time. So if you have a neutron star, okay, so due to this magnetic braking I just explained, okay, and also just mostly due to the magnetic braking, it takes about 10,000 years for it to lose all of those enormous magnetic influence to a normal pulsar. Okay, so now the current rotation period, due to the rapid spin down, magnetars typically have observed rotational period ranging from 2 seconds to 12 seconds. I mean, those ones that we have observed, their periods are much longer. So than typical pulsars that are between 1.6 to about 8 seconds, 1.6 milliseconds to 8 seconds. So now talking about milliseconds pulsar, I've explained it a little bit. So as this matter is falling in, so first of all, millisecond pulsars are the fastest pulsars in the universe. They are the most fast spinning object in the universe. Okay, their period, the time to make one complete oscillation is about 1.4 milliseconds, and that corresponds to about 716. Okay, corresponds about 716 times per second. I've explained that before. Okay, that is extremely fast. So, but the magnetic field of millisecond pulsars are just as normal as ordinary pulsars or neutron stars. Okay, so the emphasis on millisecond pulsars is on their high spin. Okay, their spin is higher than normal pulsars. Okay, so where do they get all of these spin from? So they are mostly in combined states.
Ah, the lecture is very interesting, but connection is terrible. It's terrible.
I'm almost done. Almost done. Almost done. Yeah. So as this matter fall into the pulsar, they add to the angular momentum, and that is why the speed is amplified. The spin energy, the spin of the pulsar is amplified. So a millisecond pulsar with their weaker magnetic field and efficient spin up processes rapidly display remarkably stable rotation rates, rendering them exceptional natural clocks. They are pretty stable compared to normal pulsars. So X-ray binaries, it's another type of neutron stars. X-ray binaries. So I have shown you this kind of demonstration time and time again, and I've not really explained the physics. Why is this little thing here, this neutron star, stealing matter from this huge star? I've not explained the physics behind it, and I want to explain it now. All of these things I've explained. I've shown similar videos like this, similar simulations like this. So I want to explain the physics behind it. So to understand the physics, so here is the diagram. So here is that main sequence star, that normal star. So we call it the donor star. And here is the neutron star, but we don't call it neutron star. We call it the accretor. This accretor can also be a black hole or a white dwarf. Remember, it can be these two. Now, so you have these two. Here, this black line that I've just drawn here, I was the person that sketched this, okay? Is the line join, it's just the shortest distance between these two, okay? Now, these two have their own gravitational influence on each other, okay? But if you walk along that line, if you come to this point, and I used red to mark, you would observe, so we call that the inner Lagrangian point, you will feel the same amount of force on both sides, okay? But if, for instance, this inner Lagrangian point lies within the star, so that means if these two are closer, if these two systems are closer, this line is going to come right inside the star. So it means that the matter here will feel a resultant force towards this accretor. Do you understand? So they will like to fall. They will be pushed towards this direction. But due to the system is rotating, I use these arrows to mark it. They're not going to just fall radially. They're going to spiral in. So we call this the accretion disk. Okay? So when they spiral in, they do not land at any arbitrary point, region of the neutron star or the pulsar. They do not just land anywhere they like. Because remember, as they are spiraling in, they are flowing, okay? It is not a perfect flow. They are experiencing friction. They are colliding with themselves and experiencing friction, so they are becoming charged. And as they are moving, they also have magnetic field, okay? They also have magnetic field around them. So their magnetic field will interact with the internal magnetic field of the neutron star. And so that is going to make them to land at the poles, okay? So if you can imagine that with what is happening with the Earth, when you have this mass ionic ejection from the sun, okay? Those charged particles are mostly experienced at the poles of the Earth. So we see that as a roller. So exactly what is happening here. So this accretion disk fall towards the two poles, either the North Pole or the South Pole of the neutron star, and not just any part of the star. So that is exactly. So as they are falling in, remember what I told you about infalling So for a neutron star, the mass transfer rate is about 10 raised to power 14 kilogram per transfer rate is about 10 raised to power 14 kilograms per second. Okay, so that's, as this matter is falling at 70% the speed of light, it is going to generate a power of up. So I'm trying to explain the radiation from the poles, where it is coming from. So as this matter, so the temperature that is generated when this matter is falling in is about 10 million Kelvin. And that temperature is in the X-ray. So that is why they emit X-ray. So that is the reason for the X-ray, X-ray binary pulsars. So I've been able to explain these pulses. The same for all pulsars, okay? So why you have this lighthouse thing looking thing protruding out of pulsars. I've explained it because of the infalling matter is falling at the poles, not at any part of the neutron star. Not at every part of the neutron star. So now I'm done. I'm almost done. So The above neutron star can also be X-ray binary pulsars. So binary pulsars are the roundest object in the universe. I want you to take this. Any pulsar that is in this form is the roundest thing in the universe, the round thing with the roundest circle. Have you heard of the most perfect circle before? The most perfect circle is a system of binary pulsars. So take that as a lesson from this lecture. So now how about radio quiet neutron stars? So radio quiet neutron stars are neutron stars that do not emit radio waves. They emit other higher energies like X-rays, gamma rays, even visible light, but they do not emit X-rays. So that's why we call them radio quiet neutron stars. So here is a simulation of the Crab Nebula, one of the most popular pulsars that we know. So till today, about 3,000 pulsars have been discovered and cataloged. Okay, out of these 3,000, about 30 of them are magnetars. About 30 of them are magnetars. So that will bring me to the end of my lecture. Oh, I'm so grateful. So next lecture, I'm going to be talking about white dwarfs.
Wow.
And that will be next week. I'll be talking about white dwarfs. I'll be talking about exoplanets. So I'm going to have 2 lectures by next week. So the lecture that we just had now was supposed to be for last month. So I'm going to have white dwarfs and exoplanet by next week.
Okay.
Yeah.